Hello everyone. Welcome to the second seminar of the Spanish Association of Researchers in 2021. And this time we have Dr. Miguel Méndez Isla, who is an expert of indirect detections of dark matter. But before I do any more introduction, let me share the video of the ambassador of Spain in South Africa presenting this talk.
Good afternoon and welcome to the second 2021 webinar organized by the Embassy of Spain and the Society of Spanish Researchers in South Africa. Under the title Analysis of Results in Dark Matter Indirect Searches, today's webinar is given by Dr. Miguel Alfonso Méndez Isla, Postdoctoral Research Fellow of Cosmology and Gravity Group and the University of Cape Town, together with the Square Kilometre Array telescopes collaboration. Dr. Méndez will explain to us some of the most revolutionary techniques in particle dark matter results with detectors such as the Square Kilometre Array in South Africa allows, as well as up-to-date data results in this
field. Let me stop sharing. And well, as I said, it's an honor to present to you my colleague and friend, Miguel Méndez Isla. And he did his thesis focused in indirect detection of dark matter, especially from dark matter coming from extra dimensions. And this may sound difficult, but the good thing is that Miguel also has a career in education, so he's capable of explaining these very hard concepts in a way that everybody can understand. So I think you will enjoy this talk. So without further notice, I let you the stage to you, Miguel.
Okay, thank you so much. Okay, it's a big pleasure to be here. Thanks to the Spanish Embassy in South Africa. Also, thank you to AFE South Africa for organizing this talk. As I told you, it's a big pleasure to be here. I'm gonna try to explain some of the concepts that I came across during my thesis. I hope you will enjoy. So thank you, Pepe, for this introduction. It's a big pleasure to share these ideas with you. So let me start. I'm gonna share my screen. Let me see here. Okay, good. Let me see. Let me know if you see my screen. Do you all see it?
Yeah, you can. We can see it. It's fine.
Okay, good. So as I told you, thank you so much. The title of my talk is Analysis of Resulting Dark Matter Indirect Searches. As I told you, I'm going to try to explain here some of the main concepts I came across during my thesis. I'm going to try to divide this talk into three parts. In the first part, I'm going to speak about I'm going to try to give you a general overview about the different fields we can find in physics. First, I'm going to talk about classical physics, and then I'm going to talk about modern physics. At the beginning, I was not sure to include this part, but I think that it's going to give some extra clarification for the things we will see later. And I think that this extra clarification is going to be also useful for those people who don't work in physics every day. In the second part, I'm going to try to give also a general idea about gravity and cosmology, and we will see how the concept of dark matter emerged from these two formalisms. So there are many evidence of the existence of dark matter, but I'm gonna focus only in one of them, okay? And then maybe I will explain a second one when I start to talk about dark matter halos. So we will see the rise or the emergence of the concept of dark matter, basically from the cosmology's point of view. In the last part, I'm going to talk about dark matter indirect searches. So that's I'm going to speak about the project of my PhD. So almost my whole thesis was about these new techniques to discover dark matter. So let me tell you in advance that dark matter is something that we cannot see with our eyes. It's something that we cannot detect with our telescope because it's not visible matter. So one of the questions is, how can we detect something that we cannot see? So here we will see in this third section how to detect dark matter in an indirect way. Okay, good. So let's start with classic physics and modern physics, a general overview. I would like to start just sharing with you a quote that I found in one of the most used books in mechanics for students, at least if you have studied at the Complutense University in Madrid. And the quote is the following: "Scientists are people who try to understand and experiment with nature." Why did I bring this quote here? Basically, I want to give you a starting point. So I will try to explain a little bit how the different fields in physics appeared, and taking as the ideas of this book I mentioned. So the book is Fundamental University Physics, Volume 1, Mechanics by Marcelo Alonso and Edward Finn. And the answer is quite simple. The answer they propose, it's quite intuitive. So the question is how the different fields in physics emerge, and what these authors say is that the way we have to experiment, the way we experimented with nature, and the way we understood nature at the beginning was through our senses. So, for example, through sight, we could interact with light, and from this interaction and all the knowledge collected from this interaction, optics was developed. So optics is basically a collection of the different sciences that study light, okay? In the same way, through hearing senses, we can interact with sound, and the collection of the knowledge of all these fields, all this science gave us or ended up in what we call acoustics, okay? Also, the way we experiment with heat, it's something that we call nowadays thermoreceptions. From this interaction and the study of this interaction, we got a field that was called thermodynamics. And also, on the other hand, so I mentioned some of the main fields that emerge from the interaction of humans with nature, with their senses, but also the scientists just created all other and other fields from things that were not sense related. For example, something typical as the movement. So for example, the study of the movement of the different objects in our universe can be collected in a science that we call mechanics, okay? And within this field, we have a subfield that we call gravitation, which is basically the study of the movement of objects, but not all type of objects, but celestial bodies. So gravitation is a subfield of mechanics. Good. And in the 19th century, maybe because this field is less intuitive than the rest, from the study of electricity and magnetism, the field of electromagnetism emerged. So it was discovered that electricity and magnetism are different phases of the same phenomena. So that collection of all the knowledge about these two fields was what we call electromagnetism. Good. So we have different fields here that we can group in what we call classic physics, and everything seemed to be in harmony in classic physics until 19th centuries. What I mean basically is that everything we wanted to explain about our universe could be explained with these different fields, okay? Even it was possible to include some of the fields, group them into a more general one. So for example, it was discovered that lights behave as an electromagnetic wave. So optic was included within electromagnetism, studied mainly by James Clerk Maxwell. Okay, good. And also with the help of statistics and particle theory, what I mean with particle theory is just the idea that all our universe is made up by blocks that we call atoms. I'm not speaking about a modern particle theory of physics. It's just that idea that our universe is made up by atoms. So with the help of statistics and particle theory, it was possible to include thermodynamics and acoustics within mechanics, okay? One of the most important scientists in this field is Isaac Newton. So what I told you basically is that everything seemed to be in harmony in classic physics, so we could explain almost, we wanted to know about nature with these different fields I mentioned. But in 19th century, we got a result, scientists got a result in electromagnetism, a mathematical result that was the following, that the speed of light is constant and equal to 3 by 10 to 8 meters per second. So in vacuum. So maybe you will say that this result is not impressive at all because maybe you say, okay, it's something similar to the speed of sound. It has just a value. But the important part of this result is that the speed of light is independent of the observer. So all the possible observers will measure the same value for the speed of light, independent of their state of movement. So let me show you just an example here. Okay, so let's imagine we have two situations. So in the first situation, let's imagine we have an archer that is shooting an arrow at 200 kilometers per hour. And that archer is inside a train at 100 kilometers per hour. So from someone that is looking the arrow from outside, the total velocity of the arrow will be just addition of the velocity of the arrow measured by the observer plus the velocity of the train. It's just addition of them. So we have 200 kilometers plus 100 kilometers, and the result is 300 kilometers. That's the speed of the arrow from the point of view of B, okay, here in Archer B, okay. Good, let's think about the same situation, but in this case, instead of shooting an arrow, we have a lantern, and we have someone inside the train just sending a light beam, okay? So in this case, maybe you will think that the total velocity of the light measured by the observer B is going to be just the velocity of the train plus the speed of light. But as I told you, the discovery in electromagnetism was independent of the observer. So that means that both observers are going to measure the speed of light. So the value for the speed of light is the same in all the possible frameworks. Good. So we had mechanics from Newton, and if you see here, we combine the experience with light in a situation that try to explain the movement of an entity. So here is where we see a mix in mechanics and also electromagnetism. But as I told you, in the first situation, we have that the total velocity is just the addition of the partial velocities. This is something that we observe every day, okay? And I would like also that you consider, that you remember that the velocity, remember from high school, that velocity is basically spaced over time. So this is what we have when we study physics from a Newtonian point of view. But remember also about the situation I told you in the second case. We need to take into account that all the observers measure the same speed of light independently of their state of movement. Okay, so to the idea, the Newtonian idea we had about the addition of velocities, we have to also include the second situation. So this was one of the main steps to pass from Newton's mechanics to Einstein's general relativity. Of course, there were some intermediate points between them, between these two formalisms, but this is the way we pass, or one of the first step to pass from Newton's mechanics to Einstein's general relativity. Why did I bring that velocity is space over time? Because of course we have, in order to take into account the second situation, we have to think again about space and about time. Good. I don't want to make you feel confused about this. The question is Newton's mechanics still valid? What I told you doesn't mean that Newton is not valid anymore, okay? What we have is like the general relativity by Einstein is a general formalism, is a general theory that include Newton's mechanics, okay? So Newton's mechanics is still valid, but not at high velocities, okay? When we want to study things that are close to the speed of light, we have to use, or higher energies, we have to use general relativity. Okay, so in 20th centuries, scientists started to develop general relativity, but on the other hand, something happened in thermodynamics. So what we call the ultraviolet, I'm not gonna get too much into detail here, but the ultraviolet catastrophe in thermodynamics and the photoelectric effect resulted also in a revolution that we call quantum mechanics and particle physics. So this combination of general relativity and quantum mechanics is what we call modern physics, okay? Good. So we have modern physics. Let me just speak here about gravity and cosmology and how the concept of dark matter emerged from these two theories. As I told you, gravitation is the study of movement of celestial bodies and also the cause of this movement, okay? Remember that gravitation is a subfield inside mechanics. Good. Gravitation is told you about the movement of celestial objects and its causes. Remember that the celestial objects were related at the beginning with a particular cosmovision. I'm speaking about the Aristotelian cosmovision, in which the Earth was the center of the universe and the rest of the universe seemed to be static, okay? This idea was discarded in the 15th, 16th, and 17th centuries by many scientists. Okay, we have Copernicus, Galileo, Kepler, and Newton. And what they did basically in general words is instead of just saying, okay, this is the cosmovision, they started to take some data, okay, they started to collect some data, and they did some predictions with this data, okay? So during these centuries, the cosmovision changed. Between them, okay, I would like to mention the role of Newton, basically because he didn't only he didn't only work on collecting that data, but also to give a mathematical proof for what was happening in those celestial bodies. So Newton provided a mathematical formalism to describe the movement of celestial bodies due to the action of gravity. Okay, it was not only about collecting data, but also about to provide a mathematical description of the different phenomena. These phenomena were tested experimentally, so Newton's gravity was very, very successful. Okay, and of course, I'm not gonna speak about the three Newton's law, but just let me tell you something that maybe can be a little bit subtle, and it's that Newton mechanics is a perfect tool to predict things that we cannot detect with our senses. I would like to focus on this. I would like to stress this idea because it's going to help us to understand how the concept of dark matter emerged. So let's think about two situations. In the first situation, let's imagine that we have a big planet at the center or a big star in the center, and orbiting this big planet, we have a small planet. So from the mathematical formalism, what we have is that, the mass of the big planet is proportional to the velocity of the small planet orbiting it. Okay, so maybe this is not very impressive, maybe you will say, but let's imagine the same situation, but without seeing the big planet. So let's imagine that we cannot observe it experimentally for any reason, okay? So even if we don't have any information, if we cannot see that planet at the center, it's possible to get some information of it, basically because we can observe what happens with the small planet. So we know what happens in the surrounding of the big planet. Only with the velocity of the small planet, we can have some information about the planet that is at the center. Okay, so as I told you, Newton's mechanics is a perfect tool to predict things we cannot observe directly. Okay, good. So, well, Newton's formalism was applied to several groups of bodies, stars, planets, galaxies, and one of the things we got also about Newton's mechanics is that gravity is always attractive. Okay, but in 1929, however, in 1929, Edwin Hubble discovered something a little bit different. So gravity is always attractive, but Edwin Hubble just measured the velocities of different galaxies. Okay, and what he observed is that they were moving away from us. So how does that possible? Okay, if gravity is always attractive, how is it possible that those galaxies are moving away from us? So this was one of the first results that showed us that the universe is expanding. Okay, so what we did basically is measuring the velocity of these galaxies, and he observed that the galaxies that are closer to us, they move slower than the galaxies that are far away from us. all this experience was synthesized in what we call the Hubble's law. We have here the formula: the velocity is equal to a constant by the distance of the galaxy from us. And this constant, h naught, the Hubble constant, is the ratio of expansion of our universe. Okay, so we had the result by Newton, but in 1929 it was observed that the universe is expanding. If we want to explain a universe expanding, the question is, how do we deal with the expansion of the universe? So as I told you, the discovery by Edwin Hubble was in 1929. So what we can do is just taking general relativity, because remember that general relativity at this time was developed. So we can take general relativity and we can just set we can set that our universe is expanding. Okay, so here, if you check the equations in general relativity, you see that you have many degrees of freedoms. So you have to put, before starting to do some operations with them, you have also to provide some assumptions. Okay, so we have general relativity. We want to explain the expansion of our universe, but in order to deal with this, we have to put some constraints or to make some assumptions. The assumptions to explain the expansion of the universe with general relativity is what we call, the cosmological principle, and is that our universe is homogeneous and isotropic. So this, in general words, means that our universe look more or less the same at any point of it. So the universe is quite similar at each location of it. Okay, so this is what we call the cosmological principle. Maybe you will say, okay, this is not true. If I look at the center of the solar system, I can see the sun, but if I see toward the other direction, I just see some stars. So the universe is not different, it's not homogeneous, it's not isotropic. But from some observations, okay, by AAO, if we look our universe from a large distance, this is the image we have, we can observe that our universe is more or less homogeneous and isotropic. So this is a good starting point. Of course, there are some different research groups that try to see also deviations in this cosmological principle, but this is the starting point to have a Big Bang theory. So remember, we have general relativity. We also plug here some assumptions. We say that our universe is homogeneous and isotropic. This is what we call the cosmological principle. Okay, and what we get from this combination of general relativity assumptions and universe expanding, what we call the Friedmann equations. There are more than one, but I'm gonna focus only in one of them, okay? So what we have basically, this is H0. Remember that H0 is the ratio of expansion of the universe nowadays, okay? This is the constant I showed you before in the Hubble's law. And what we get here, okay, within the Friedmann, in the Friedmann equations is the ratio of our universe at any point in time, okay, at any time in the history of our universe, okay. So what we can have here is just the ratio of expansion of our universe at any time. Okay, so this is very useful, not only because we want to know the ratio of expansion of our universe, because also the behavior of matter and energy, the content of the in the universe, the content of the universe is also constrained by the expansion of it. Okay, so the expansion is going to put some constraints in the way energy and matter behave in our universe. Good. Let me see. I'm not seeing if there are questions here. I'm so sorry. Okay, if there are questions, please let me know, because I don't know. I cannot see. Sorry, I cannot see.
There are no questions left. If there is anyone, I will let
okay, just let me know. Thank you so much. Good. So we have here the ratio of expansion of our universe. This H depends on time. So, and what I would like to focus on here is that the ratio of expansion of our universe depends on these four constants. Okay. So this is, so if we set these constants in general, okay, if we set this constant, we will know more or less how our universe is expanding. Okay, and these constants are the density parameter for matter, the density parameter for radiation, the density parameter for the universe curvature, and the density parameter for dark energy. So the ratio of expansion of our universe is gonna be determined by these constants, okay? The density parameter for matter is also, in general words, the density of matter, the amount of matter or the content of matter there is in our universe. The density parameter for radiation is the content of massless particles we have in our universe, like for example, photons, okay? So all the radiation will be included in this parameter. Density parameter for the universe curve tells us the shape of our universe, and the density parameter for dark energy accounts for dark energy that is it's taken basically to explain the accelerated expansion of our universe. So we really don't know what this parameter is, okay, dark energy. We don't know what dark energy is, but we know that we need it in order to explain the acceleration in the expansion of our universe. Our universe is expanding accelerated. Good. So we have some different constants here. For constants, as I told you, how do we measure them? We have two ways to measure, to set these constants. One of them is through the CMB, cosmic microwave background. So as I told you, it's possible to set these parameters, and one of them is through observing this radiation. So it's a radiation that it's in the whole universe, and by studying this radiation, we can set some of the parameters I showed you here to explain the ratio of expansion of our universe. So the CMB is the most ancient light received from the early universe, okay? So this is the oldest light we received from the Big Bang. It was measured mainly by the telescope Planck. So this is the first light of the Big Bang, and if we with the observation of it, we can set some of the parameters you see here. Good. The other way we have to determine those parameters is through what we call the Big Bang nucleosynthesis, or BBN, okay? Big Bang nucleosynthesis is a mathematical formalism to explain the formation of the atomic nuclei. So taking into account the thermodynamics of our universe at the beginning, so it's possible to know how the different nuclei were formed, okay? So this is, as I told you, is a mathematical formalism that we can compare also with the different abundances of the chemical elements we have in our universe. So we can compare this mathematical formalism with what we observe nowadays. Okay, so from these two ways, from these two set of experimental data from the CMB and the BBN, it is possible to constrain the density parameters I showed you here. It's possible to know the content of our universe. Good. This is the result when we set the parameters of our universe when we measure those parameters, and 69% is what we call dark energy, which is referred to the omega. I show you the dark energy, the omega I showed you before. Then 25% is what we call dark matter. So remember here that we have an omega matter, okay? And then we have here, okay, so we can determine the omega matter with the cosmic microwave background, and we can determine also the omega matter by Big Bang nucleosynthesis. Big Bang nucleosynthesis, that, remember, that mathematical formalism that explain how the atoms, how the nuclei of our universe were formed. When you determine that constant by those two methods, you realize that the value of this omega don't coincide, okay? When you use those two methods, both values don't coincide. So that means that some of the matter we have in our universe does not correspond to atomic nuclei, okay? So yes, so this is what we call dark matter. Dark matter is a kind of matter that does not belong to, let me say, normal matter, or let me say atomic matter, okay? So everything we see in our universe is, or everything we observe with light in our universe, okay, is what we call atomic matter, is, let me say again, normal matter, but there is an amount of matter in our universe that we cannot observe, okay? And this is what we call dark matter. So that part of the matter that does not correspond to the value in BBN. So that means that it doesn't correspond to atomic nuclei. Good, so we have, as I told you, 69 is dark energy, 25 is dark matter, and 5% is atomic matter. So basically everything we observe in our universe is just a 5%, okay? The rest is something we don't know, okay? The 25% that corresponds to matter, and 69 that corresponds to dark energy. Okay. Let's focus on dark matter. So from our, as I told you, the agreed, well, as I told you, dark matter does not correspond to, let me say, normal matter or usual nuclei, and dark matter does not interact electromagnetically. So it's not a visible matter. It's not the normal matter we observe. So there should be a kind of matter we cannot observe, and it's not part of the normal matter we observe in our everyday life, okay? So these are the agreed characteristics for scientists, which is dark matter does not correspond to normal matter, and dark matter does not interact electromagnetically, okay? So it's not visible matter. Then it's possible to I mean, it's dark matter has also some characteristic. Not everybody agrees on that, but they are suitable for to fit in our Big Bang theory. One of them is that dark matter is made of weakly interactive massive particles. So one of the suitable characteristics for dark matter in order to fit to our Big Bang theory is that dark matter is made up by particles that they interact in a weak way with the rest of the universe or with the rest of the particles we know, and they should be massive. So the mass of those particles is quite large if we compare it with the rest of masses of well-known particles. Okay, so here we have the characteristic: normal matter or usual dark matter does not correspond to usual nuclei. Dark matter does not interact electromagnetically, so it's not visible matter. And suitable characteristics is that dark matter is made up of WIMPs, okay, weakly interactive massive particles. Okay, and what I told you before is that we need dark matter to explain the expansion of our universe. We know that we explain it through a parameter that it's in the Friedman equations, okay? But the question will be maybe, okay, we know that we need dark matter to explain the expansion of our universe or to explain the ratio of expansion of our universe, but where is that dark matter? Because everything we said till here is that it is just a parameter. So just let me rescue here that one of the things I told you before from Newton mechanics. Remember that example I showed you that about the big planet and the small planet, the small was orbiting around the big one. And I would like that you remember also that if we cover the big planet, the center, even if we don't see that planet, it's possible to know its mass, basically because we know the velocity of the planet surrounding the big one. We know the velocity of the small planet, basically. So remember this idea and remember the question, where is dark matter? Okay, so in 1939, okay, the studies by Fritz Zwicky and other scientists, okay, what I'm gonna explain was not exactly what Fritz Zwicky did, but other scientists after him. So they started to study the mass of the different galaxies by observing the velocity of the stars that conform that galaxy. Okay, remember that we can get the mass of the galaxy just basically seeing how the stars are orbiting around it. Okay, so if we have the velocity of the stars, we can get the mass of the galaxy. So what they did was just get the mass of the galaxy by seeing the rotational velocity of stars, and they compare that value with the mass or expected by by detection of visible light. So in astronomy, there is another way also to infer the mass of a galaxy by just looking the light that galaxy emit. And what they observed is that the mass that was measured through the velocity of the stars was quite large in comparison with the mass they measure by detecting the visible light of the galaxy. So the mass required to explain the rotational velocity of stars in galaxies is quite larger than the observable matter. Okay, so this idea also was a beginning to think that maybe dark matter is forming halos in which galaxies are immersed. Okay, so the idea is basically we have a galaxy in the center, and that galaxy it's surrounded by a dark matter halo. Remember that dark matter halo, according to what we said before, is made up by weakly interactive massive particles. Good. Okay, now I'm gonna focus in the third part, dark matter indirect detection. This is part, as I told you, here I'm gonna explain one of the main techniques I use to detect dark matter in these dark matter halos. So I'm gonna also explain a little bit about what I did during my thesis. Okay, dark matter indirect detection. Let's go. Well, what I told you, so dark matter is one of the assumptions is made up by WIMPs, okay, that are in dark matter galactic halos. And sorry, the question here is, how do we detect that dark matter? How is it possible to detect something that we cannot observe? So we said that dark matter is not made up by atoms or nuclei on well-known particles, and that we cannot see it electromagnetically. So the question is, how do we detect something that we cannot see? When I say see, I mean, how do we detect something that we cannot observe with our telescopes? So here I'm going to speak about one of the assumptions for dark matter, and is that dark matter annihilates. Okay, what is annihilation? Let me explain it briefly. Annihilation, this is a phenomena that happens to all known particles in physics, and it's the following. Sorry. Let's imagine we have a particle and that collides with its antiparticle. Okay, so when a particle collides with its antiparticle, what happens is that the annihilation occurs. Okay, and those particles, the result of the annihilation of two particles is or radiation, okay, let me call it like that, or also other particles, other particle, antiparticle. Okay, so remember, this is a phenomena that we observe in all the particles. We know in physics, particles and particle and antiparticle annihilate to give some photons, or let me say some radiation, here gamma rays, or also they can annihilate to give another particle and another antiparticle. So this is annihilation. This is something that happens in the physics we know. Okay, so what we suppose here is it's the same for dark matter. So if dark matter is made up by particles and those particles annihilate, we will be able to receive some radiation from that annihilation. So we said dark matter is made up by particles forming halos in which galaxies are immersed. Let's include that ingredient in which dark matter annihilates. So dark matter annihilate with the dark matter antiparticle, and then we'll be able, and they will, sorry, they annihilate into radiation or other particles. Okay. The radiation and those particles, the result of the annihilation, okay, the product of the annihilation will travel along the galaxy to different parts of the galaxy. Some of those particles will reach the solar system. We have there many detectors, so it's possible maybe to catch or to receive some signals from the annihilation of dark matter. Okay, so remember, dark matter annihilating into radiation or other particles. When I mean other particles, I mean a standard model particles. So they are particles we can observe. So we, in that annihilation, we pass from the dark sector to the visible sector. Dark matter annihilates to give, as I told you again, radiation or electrons, positrons, protons, antiprotons, neutrinos, things we can detect. Okay, good. So the products of dark matter annihilation propagate and reach the solar system after traveling. If we have here detectors, as I told you, we will be able to measure a dark matter signal. Good. So the objectives of dark matter indirect searches is just detecting signals from the space, okay, with different detectors like the SKA that measure radio frequencies, IceCube that detects neutrinos, or AMS that detects cosmic rays, okay? So the objective is detecting signals from the space, okay, and comparing this experimental signal with theoretical models, okay? So we have some theoretical models of dark matter, and we can compare those theoretical models with the signal we detect from the space, okay? Remember, because of the annihilation of dark matter. Cool. So how do we constrain dark matter then? So we have, remember, the experimental data and also the theoretical prediction. And what we do basically is just we have many strategies to see to get some information about dark matter. So, for example, one of the ways I used during my thesis is excluding models that are not possible by the comparison of the experimental results with theoretical models. So, for example, here in the first plot, we have in green the background, okay? We need a model for dark matter, but also a model for the background. That means that our telescope not only detects signals from a possible annihilation of dark matter, but also from other astrophysical sources. For example, supernovae, pulsars, different spallation of cosmic rays. There are different astrophysical sources that are there that we have to take into account. So in this case, in the first plot, we have a model of background, okay? And what we do is just plug in our model of dark matter here. So the signal from dark matter, we have two signals. One of them is this dashed dot line in pink, and we have also a dashed dot line in orange. So to the background, we include the dark matter signal, okay? So let's see the signal in pink. So the total received signal, okay, if we include to this the dark matter signal, if we include the background, the total signal is gonna be this pink line here, okay? What we say is the following: since the received signal is under the experimental data, we don't exclude this model because maybe there's another source that we are not taking into account, okay? So this model is not excluded, okay? But let's see the second situation for a model of dark matter with a mass of 41 TeV. So to this model of background, we include the signal from dark matter, and what we get is that the total signal is this one here. So since the theoretical model exceeds the experimental data, we exclude this model. We say this model is not possible. Okay, so we do more or less the same for all the possible parameters for dark matter. Here I have two parameters, the mass of dark matter and another parameter that comes from extra dimensional dark matter theories, that is the what we call the tension of the brain. So we tune these parameters and we observe if those models are excluded or not. And we can get a plot like the plot you have on the right side, okay? The color part in this plot tells you all those models of dark matter that cannot be possible, okay? So what we get is what is called an exclusion plot. So we have different models, not only of dark matter, but also of the propagation of the products of annihilation. So there are some different things that make that make things like a little bit more complicated, but the general idea is what I told you. Okay, just see if the theoretical model exceeds the experimental data. Good. And okay, and one of the way I excluded dark matter is through radio frequencies. So dark matter annihilating, and the final state of that annihilation is radio waves, okay? So there are some things in the middle that I'm not gonna explain, but what you get at the end is radio waves, okay? So during my thesis, I tried to constrain dark matter with the Square Kilometre Array. As you know, the Square Kilometre Array is a worldwide project in which many countries participate, and is, of course, is a set of radio telescopes. One part of those telescopes are in the Karoo Desert in South Africa, and other part of those telescopes in Australia. So the main thing is calculating if the SKA is going to be will be constrained dark matter. Okay, will be, if it's possible to constrain dark matter with the SKA. Okay, the main technique for the SKA is what we call the radio interferometry. In general words, also, let me tell you that some of the things that you expect from a telescope to detect signals, in general words, is good sensitivity and high resolution, okay? The high resolution is something that we can improve with what we call the radio interferometry. That means that, okay, let me just explain that, yes, the resolution of a radio telescope depends on the diameter of the dish of the telescope. So if the diameter of the dish of that telescope is larger, the resolution of the image you are gonna get is better. It's gonna be better. Okay, so the resolution depends on the diameter of your telescopes. Of course, there's gonna be a limit when you build your telescope. There's gonna be a limit for the diameter of your dish. You cannot build a dish as large as you want. So the way scientists have to solve this is, instead of only building one antenna, what they do is building different stations, like a large station with different antennas in like a huge antenna. If you see this picture here for one of the station of the SKA, you have many antennas, and now the resolution of your telescope is not gonna be referred to the diameter of the dish, but to the baseline of the station. The baseline here is the distance between the different dishes of your station. So if the baseline is larger, then the resolution of your telescope is gonna be higher, okay? Well, in this case, we have also one of the possible dispositions for the SKA, the shape of the different the stations, like conform a spiral, basically to take advantage of the rotation of the Earth when they collect data. Okay, so as I told you, first resolution, here we compare the resolution of the SKA with other different radio telescope. You will see that the SKA is one of the highest resolution. Okay, you see here. By the way, we have here the project in Australia, the SKA low. The low here, the project in Australia has a low frequencies antennas, so the range of detection in frequencies is lower than the range of frequencies in SK mid. Okay, that accounts for a mid range of frequencies. Okay, so this is the project in Australia. This is the project in South Africa. Okay, so what I told you, we have to check the resolution of our telescope. The radio interferometry is a good way to solve the resolution of our detectors. And the other thing I told you is we will like that telescope with high sensitivity. The sensitivity of the SKA is gonna reach 1 nanojansky here. Okay, so this is the quantity we see when we detect a signal. And in this plot that I have here, we can compare the resolution of the SKA, okay, with other telescopes, not only radio telescopes, but also telescopes in X-ray. Okay, so the blue band is the SKA, and you see here the sensitivity reached by the telescope. This is SK1. You will see later that we expect more phases for the SKA. Okay, and this is the sensitivity. Why is it important? The sensitivity tells you the limit in which you catch a signal and in which you only detect noise. Okay, so under the sensitivity of the telescope, what you do is considering a noise. Okay, so if your signal is less than the signal that is set by your sensitivity, you cannot say that you receive a signal but noise. So in this case, it's very important, the sensitivity of your telescope. Basically, remember, because dark matter interact weakly with the rest of particles, and the signals that we get from the annihilation of dark matter is quite weak. So you will expect a high sensitivity telescope as the SKA. Yeah. Okay. These are some of the results we get in our work, basically. So just let me tell you some technical details here, just for those of you who are interested in. So basically what we have done is calculating the density of radiation due to the annihilation of dark matter into different channels, okay? And also we saw some different masses for extra-dimensional dark matter. So what we have done is calculating this magnitude here, this quantity here, okay? And we didn't focus on the Milky Way, we didn't focus on the annihilation of dark matter in the Milky Way, but on dwarf spheroidals. Why dwarf spheroidals? Basically because we wanted to control the background of our galaxy. So we expect low background in dwarf spheroidals, so what we have done is just focusing on that. Of course, what we observe is the annihilation of dark matter into electron-positron. Those electrons-positrons will travel along the galaxy. will travel along Draco due to the interaction with the magnetic field. Those electrons also will, or positrons will also emit synchrotron emission due to the interaction with the magnetic field. This is the model of the magnetic field. And the synchrotron emission we receive is that the signal we will catch with the SK, okay? The dark matter we consider in our work is the Navarro-Frank-White halo, and the target, this result, although we took into account some other targets, this result is for Draco dwarf spheroidal at 80 kiloparsecs away. Here, the blue band refers to SKA 1 low, and the orange line is for SK 1 mid. We also consider here the field of view of the SK, and also we consider the angle of Draco here. Basically, when we calculate this signal, the channels we consider also were dark matter annihilating into quarks, going to electron positrons, and then dark matter annihilating into bosons, going to electron positron, and then also dark matter going to leptons and going to electron positron. Good. So this is what we get. The prospects for the SKA. It's basically what we plot here is the mass of our model, the mass of dark matter, the mass of the WIMPs against the thermal average cross section. So we consider thermal relic densities, and we have here the maximum mass that the SKA will discard. Okay, so for example, for the SK1 low, the maximum mass that the SKA is able to exclude for an exponential magnetic field and for dark matter annihilating into tau minus is 190 TeV. For the case of W plus W minus is about 70 TeV. For dark matter annihilating into BB bar is 9.36. In the case we see in this table that we will get better constraints with the SK1 mid in South Africa. The maximum mass able to exclude for the SK1 is 2.87 for tau plus tau minus, for W plus W minus is 11, and for the channel BB bar is for about 14 TeVs. Okay, and what we expect for the SK, all these constraints were done for the SK phase 1 here. Okay, we have here all the SK pathfinders, all the SK precursors. We had CAT7, 7 antennas. The baseline is 185 meters, and this project was completed in 2010. Then we had the second phase was MURCAT, in which we had 64 antennas and a baseline of 8 kilometers. This project also was complete in 2018. For the SK1, which is the stage we are now, we have about 200 antennas and a baseline of 150 kilometers. You see the difference between MURCAT and the SKA. The project will be completed in 2023, and we expect also a second phase for the SKA, which is SK2 with 2,500 antennas. Yes, the project is expected to be complete in 2030. So it will be possible to set in better constraints for dark matter with the SK2. Good. I would like just to finish telling you that the SK is a worldwide collaboration. I would like also to thank you not only for your attention, but also for make these collaborations possible. Spain and South Africa are part of this worldwide collaboration, and I know that groups as ACE South Africa and the Spanish Embassy work very hard to make these collaborations possible. Just let me finish showing you one of the pictures caught by the SKA about the center of our galaxy. Is a high resolution picture. And yes, thank you. Thank you so much for your attention.
Well, thank you very much for this very illustrative talk. And I will see if there is any question. Or in the chat.
Let me see. Sorry.
Meanwhile, we wait for some questions. Let me ask you one that I have. That is, what do you think is our best chance to detect dark matter?
Well, let me show you something, Pepe. Again, sorry. Let me just go again to the presentation to show it to you here. Okay. Here. Okay, here. Okay, good. One of the things that boosts a lot the dark matter signal is the dark matter density profile. I'm gonna show it to you now if I find the presentation, and I don't know if you see it. Okay, so one of the main questions for dark matter is how dark matter is disposed in those dark matter galactic halos. So depending on how dark matter is in the galactic halos, we will receive more signal or less signals. One of the things we have to see if dark matter form spikes, okay, in their density profile. If you have a spike in the density of dark matter in the galaxy, what happens is like there is a boost in the signal you receive because the probability of annihilation is greater in that spike. Okay, so one of the way also to form those spikes is to see the influence of black holes in dark matter halos. Because of the gravitation, the black holes will be able to attract dark matter particles, increasing the probability of annihilation and increasing also the possible signal you receive. So I think that checking how dark matter behaves around black holes is it will be a good step to follow.
Okay, that's very interesting.
I don't know if I answered your question.
Yeah. I just wanted to know, where this detection or dark matter are going in the future, apart from building larger and larger telescopes.
Yes, larger and larger telescope. Yes.
So I think there are no more questions. So I'm gonna end the recording here.